Okay, let's talk about vector fields. So I can give you an example of a scalar field, not a vector field. I'll give you an example of a vector field soon. But an example of a scalar field is, let's say you have a map of Oklahoma. And at each location, I'll tell you a temperature. Let's say 93 degrees, 84 degrees, 77 degrees, right? This is a scalar field because it's a field of associated numbers to each point here, because we can think of that as on some xy plane, right? So for every xy, there's some associated scalar number at 84, for instance. A vector field is very much like that, except instead of for every point you have a scalar, for every point you have a vector. Something like that. Let's say this is like wind currents that are going on in Oklahoma, velocity speeds, so of wind. So yeah, the Panhandle is getting a lot of wind. But here in Oklahoma City, the wind is not that much, for instance, You have associated vectors that say, okay, over here, let's say in Edmond, the wind is blowing in this direction at 30 miles per hour. Okay. So the definition of a vector field on R2. A vector field F on R2 is a function that assigns for every xy element of R2 a vector v. So f of xy is some v. So for every xy coordinate we have here, there's some associated vector v. You guys see like wind current maps that have like a bunch of arrows and stuff like that? It's in your text, and it's really hard to like reproduce such beautiful images by hand. It takes some time and some effort. Let's see here. Yeah. So these are wind currents right here, where all the vectors are the same length, and then they represent different magnitudes, like different colors. That way, like one vector isn't imposing onto the location of another vector, like I have here. So yeah, these are very useful. This kind of mathematics of calculus is extremely useful. I mean, it's used in airfoils and aerodynamics for the wings of airplanes. It's used in ocean currents. It's used in fluid dynamics and fluid mechanics. It is very useful. Okay. So now that I've kind of introduced you to the concepts, okay, we notice that if this is equal to some v, then that implies that our vector f of xy, if we write it in component form, can have a function of xy in its x parameterization and a function of xy in its y parameterization. Notice that this is the same thing as this. where P and Q are functions that model how does the X parameter change and how does the Y parameter change. And it's a function of your X and Y, which is for each point, these will output various values. So for here, for example, here, for that X, Y, Q is, P is 0, right? Q is some value. Let's say if I give it, let's say 30, then this would just be 30 J hat. It would be 30 J hat at that point. Let's say this is 4, 1. So F of 4, 1 would equal 30. And not just 30 because that implies it's a scalar. It would be 30 J hat, right? So that's trying to tie it to the real world. Now, but we exist in Calc 3 and we exist in 3 dimensions. So we can define a vector field on R3 very easily. It's just like this. On R3, your vector field. It doesn't even have to depend on Z, but it can. It will just be like this, some P of right? So let's give an example here. One that will, as you will see, correlates to magnetic fields and their effects on charged particles. Who here's taking physics? You guys remember talking about magnetic fields and the effects of a magnetic field on charged particles? Do you remember what magnetic fields do to charged particles? No? Okay, that's fine. It's really cool. Raise your hand if you know or have seen the Aurora Borealis, if you know about it. You know about it?
I've heard of it.
But you never seen it? I want to go see it. Okay, so the Aurora Borealis is caused by charged particles coming from the cosmos or from the sun, and they hit the Earth's magnetic field. Here's the Earth, and it has magnetic field lines that look like this. They go out like that. The reason we here on Oklahoma can't see the northern lights is because the magnetic field stretches out really far. But over here in Iceland, where I totally want to live, I want to live in Iceland because I like the cold, and I like the northern lights, even though I've never seen it. Over here, the magnetic field is more penetrable, and charged particles from the sky rotate in the magnetic field. So, as you will see, what I'm about to show you correlates to the Aurora Borealis. It's going to correlate to what charged particles do in a magnetic field. But you don't see that yet, but I'll show you. Let's say we're given a vector field, like so. That's our vector field. On R2. Okay. Let's describe it. All right. Well, what we want to do is we want to plot something, but we don't know what to plot. So what we'll do is we'll evaluate the vector field at various points. What about like 0, 0? We trivially get the 0, 0 vector. So over here, there's nothing going on. What about, let's say 1, 0? Well, 1 is X, so we get a 1 here. 0 is Y, and you get a negative 0, which is just 0. So at 1, 0, let's come over here, 1 on the X, 0 on the Y, we have a vector 0, 1, meaning it just points straight up. It's by 1 unit. All right? So it's generating at that point, at this point, 1, 0. It's generating this vector 0, 1. Let's continue our analysis. Vector field, let's say, what is it doing at 0, 1? Like right here, 0, 1. Well, the y is -1, the x is 0. So over here, it's creating a vector that points down, to the left, right, by 1 unit, and none down, right? Because that's the x, and that's the y. And this is the location, 0, 1. Let's then see what else is it doing. We're picking test points on the two-dimensional space and seeing what is a vector doing there. Because every point, I'm not going to list all of them, but every point will have a vector associated to this vector field. What about at 1, 0? This point right here. I should do 0, I should do -1, 0. Y is -0, so it's just 0. And this becomes -1, because that's what your x is from your function. So now over here, what we'll have is actually we'll have a vector that just points down a unit amount. And you can see and do it for here, you have a vector that goes like that. So you notice you have like a vector field that at every point that as you go out farther and farther in concentric rings, you'll get a vector that is pointing perpendicular or tangent, if you will, to the circle. It's tangent, not perpendicular. Tangent to various circles of various radii. Any circle, pick a circle with the radius, this vector field has tangent vectors to that circle. As you'll see, this is actually what a magnetic field does to a charged particle. Let's say this is an electron. The magnetic field will put a force on it perpendicularly and cause it to spin. So what happens when something is spinning but is falling? It coils, and charged particles radiate. Who here has ever wondered what is fire or what is light? Why is light happening? Yeah, everybody wonders that, especially when you're little kids. Fire is a state of matter called plasma. Plasma is when the electrons on an atom are no longer strongly linked to it. The force is very weak. Right now, the atoms on this table are holding on to their electrons really well. They're not letting them go. But when they're starting to let them go, what happens is they glow and they become a plasma. So fire is really a plasma, and it's a plasma of gas. The gas has actually let go of its electrons, and so an electron is a charged particle. Because it moves and it accelerates, it radiates light. And so that's what fire is. It's a bunch of electrons that have dissociated from their atoms, their gaseous atoms, and now they're radiating light. And this is what causes the Aurora Borealis. When charged particles fall into a magnetic field, they start to coil. And that's what they radiate, that glow that you see in the Aurora Borealis. And it happens down here too. I believe the Aurora Australis as well in Australia. Really cool. But this vector field actually models something that's not even like magnetism, but it is in electromagnetism, as we'll see in the next following examples. So we modeled and described a vector field. You guys are going to have to do the same. You just get your vector field that you're given, evaluate some points and what kinds of vectors they have, and draw it. Then you get like a visual representation of what that vector field it looks like. All right. What about another vector field? Let's do a three-dimensional vector field. What about if I have this? Z. What does this vector field look like? Well, we do the same thing. Let's pick a point and see what the vector field is doing there. Let's start at the origin. What is it doing at the origin? This rule tells us nothing. It's not doing anything at the origin. What is it doing at, like, let's say, here? Nothing. It's not doing anything there. It's not doing anything here at all. At 1, 0, 0. Nothing going on here, nothing going on origin. Well, is there anything going on with this thing? Well, actually, yeah. If I plug in a non-zero value for z, we will get a vector to show up. So what about, you'll get this vector. And what about this? See what's going on? So here, at let's say 0, 0, 1, we get a vector that points in 0, 0, 1. So that means it's pointing just straight up, unitally. What about at 0, 0, 3? Okay. Here's 1, 2, 3. At 0, 0, 3, it's pointing up 3, but it's going straight up. And so over here, what about at this point? Let's say this is 0 for x, 1 for y, and 1 for z. It'll point up 1 in the z direction at this location. And over here, it'll point up 2 in the z location. What about over here at negative z's? Let's go down here to the negative 3 on the z-axis. All right. Over here, then it's just pointing down negative 3. So you get a vector field that looks like this. Where the higher you go, the longer the vectors get, pointing straight up in the z direction. And the lower you go, the lower they point and higher magnitude. And they'll do the same over here. And we'll figure that out just by putting some test points and realizing our vector function is defined like this. So you get some really cool pictures out of this stuff. Okay. Some of the applications of these vector fields, and we'll get to this, I will get more to electromagnetism here, about the Aurora Borealis, is in fluid dynamics. So let's say you have a pipe of increasing radius. You can, or various radius, you can model how the fluid flows in it. Using vector fields. And these specifically are velocity fields. Okay. But there's more. There's more. We could talk about the gravitational field for the gravitational force field. So there's velocity fields. There's force fields. Why they're all vector fields? Well, because gravity, the force of gravity is a vector. So there's a gravitational force field right here, right now. That's why this is happening. Okay. So in the gravitational field, Newton's law of gravitation says that, what do we want to do with that the magnitude of the force of gravity is the gravitational constant times the first mass times the second mass divided by the distance between them squared. This is Newton's law of gravitation. Okay. But that's just the magnitude. What if we wanted the vector? Well, if we want the vector, then we want to know in what direction, because this is the magnitude. And vectors have magnitude and direction. So we attain its direction by just taking the unit vector value of the force. So the unit vector of that is, we just get divided by its own magnitude, right? Notice that given our vector, let's say we have a position vector, okay? And it's parameterized by some x, y, and z. And we want to know what is in this position, what is the value of the force field, okay? We can then say that, oh, r in this equation is the same thing as the magnitude of the position vector. Because let's say in three-dimensional space, we got the position vector here. R would just be equal to the distance from this point to the origin. Because we can always set one of the masses here at the origin and have another mass over here. Or we could just say, even if we didn't have a mass, in the presence of one gravitating body centered at the origin, what is the gravitational force felt by this point P from that origin? So we notice that if R is equal to P, then when the magnitude of P, that means R is equal to the magnitude of P is this, the distance away from the origin of that point. So R squared is this. So we could change this formulation to look like that. And in 3 dimensions, okay, I'll get to what it's going to do in 3 dimensions. Okay. First, we'll note that what we wanted to do here is we wanted to unitize a vector. We don't want to unitize a force vector. We want to unitize a position vector. Because that tells us in what direction is it going. So what we're going to be doing is getting this. So rewriting this equation right here, we get gravitational constant, mass 1, mass 2, divided by, instead of r squared, we're going to have this x squared plus y squared plus z. Actually, let's just keep it as instead of r squared, let's have it magnitude of p squared, since r is magnitude of p. Okay. Then for it to be a vector, it's missing something because this is just purely a scalar. For it to be a vector, there needs to be a vector here, and that is precisely this unit vector here. So notice when you do that and then you simplify, what you get. Which is very interesting how there's a cubed term showing up. Now it's a full-blown vector. Before it was just a scalar. And so when you write it out to get the three-dimensional expression for the gravitational field, the gravitational force field, the vector field for the gravitational field, and the gravitational force will be what's up with that 3/2 business? Well, that's because, remember, magnitude of P to this is equal to this. So when we did magnitude of P cubed, what we're just doing is cubing both sides here, raising it to the third power. And so that's why you get the 3/2. And it's in the denominator, and that's why the 3/2 is showing up in the denominator. And this is a three-dimensional expression where, remember, this was your T of XYZ. This is your Q of XYZ. This is your R of XYZ. And this is your F of XYZ. Just like how we defined it before. This is the gravitational vector field that gets generated. Well, and there is one more addition to it. This would represent repulsive gravity, like in dark energy, right? But this is actually, we want to talk about gravity that is attractive. So we must put a minus sign on it. So let's not forget that all of these actually need minus signs. Why? Or else our mathematics would say that gravity just pushes things. And like this thing would fly up and we'd all fly up. We all just shoot off of the surface of the earth. Existence would not be possible. Everything would just be ejected off of the surface of things that have lots of mass. It's the opposite though. Things that have lots of mass attract and hold, and they stabilize. So that means the gravitational field looks like this. Bunch of vectors pointing to the center. Who here wondered when they were little kids, why are all the planets like balls? Why are they like spheres? You wonder that? I wondered, why isn't there any planets that look like, cubes? Why isn't there any planets that look like triangles? They're all just spheres, right? Why is that?
It's got the same force pushing down on every part of the surface.
That's right, 100% correct. That's because the gravitational force just pushes it towards the center, everything. Everything is just being pushed towards the center. Everything, everything, everything. So what happens when you do that is you get a spherical object. Because when all the matter deposits, it forms a sphere. That's why. Why does gravity do that? We don't know. All that we know is that it just does. for now. For now, we don't know why it's doing this. We just know that it's doing this. Let's talk about electric force fields now. I'm telling you, this is when math, math is already cool. I'm one of those people who, I don't think physics is cooler than math, and I don't think math is cooler than physics. I think they're very cool. Both of them are equally cool. But math is truly really cool. Also, when you apply it to real life situations like this. Okay? And now we can apply it to another real life situation, an electric field. Who here knows or has heard of an electric field? You heard of one? Do you know what an electric field is? No. It's a vector field. It's a vector field. And we're talking about vector fields. So let's talk about electric force fields. So let's say we have a charge Q located at the origin. What do we mean by a charge Q? Well, we just mean it's a particle that has a charge. What is charge anyways? It's just something human beings have associated to particles. We just, through experimentation, noticed that some particles have this property and other particles have another property. Why don't we just call that property charge and say that these things have positive charge and these things have negative charge? It's like a bookkeeping technique. Who here has played with magnets? You know there's on magnets, two sides they hold, and when you flip it, then they'll push away. That's how this stuff got invented. People were playing around with stuff, and they said, when I align it this way, they attract. Let's say that, that's one kind of charge. Positive, whatever. It's not necessarily that. But then when we flip it and then they push away, let's say that's negative. They don't like each other. They're trying to push each other away. They have a negative relationship. Whereas when you flip it, they come close. They like each other. The magnets like each other. It's a positive relationship. It's as simple as that, how human beings came up with charge and association of charge. Then we started to assign some mathematics to the concept to try and quantify, okay, given the fact that there is this charge, how does it interplay with different parameters of nature? Okay. So suppose a charge is located at the origin. At some point, here's the point x, y, z, and here's the vector p, where clearly, because p is a displacement vector, it's this. What do I mean by that? It's a displacement vector with regards to the origin. So you just get that. So p is really a displacement vector, but it's really a position vector. Coulomb's law. Coulomb's law states that the force of an the electric force between two charged particles is some constant epsilon times your first charge q times your second charge q, everything divided by the distance between them. That's the magnitude. Because what we have so far is a scalar quantity. How do we make it a vector quantity? Well, that's all dependent on the charges. In electricity and magnetism, when you have a positive and a negative charge, the force is attractive. So if Q is positive and capital Q is negative, then the force is attractive. So Q negative, capital Q positive would imply that the force vector would be attractive, so we put a minus sign on it. And vice versa. Little q could have been positive and capital Q could have been negative. It would still be an attractive force. What about when the force? What about when they're the same though? If they're both, let's say, positive. Or let's say they're both negative. Oh, then the force is repulsive. In both those cases, right? And notice that the sign comes up here. We also have to multiply it times our position vector divided by its magnitude, just like last time. And just like last time, like with the gravitational field, we could just say let R equal magnitude of the position vector. That means R squared equals magnitude squared. And that means the magnitude of the position is still this. So you would get something similar to the gravitational one. And your equation would similarly, when you switch it from R to P's, you get this. Just like in the gravitational derivation. And whether this is positive or negative depends on what your charges are, if they're positive or negative. So now let's talk about gradient fields. Oh, wait a second. Did I? Yeah. So I'm not done with this yet. This is to talk about the electric field. Electric fields are force fields per unit charge. So per a charge, the force field becomes an electric field. And that is what we have over here. Because when we multiply this by 1 over q, the q's cancel, and we get that. Now I can talk about gradient fields. In lab, you guys will generate force fields or vector fields, and Maple will create cool ones. It'll have a lot of details to it just through some button pressing. What's a gradient field? All right. Let f be a scalar function. Then the gradient of f, defined to be this, partial f, partial x, partial f, partial y, partial f, partial z. This forms a vector field. Specifically, the gradient field. What is this? Well, for every point, For every point, we can evaluate this vector. Let me give you an example. Let's let f equal x plus y plus z, something simple. Then the gradient of f will equal 1, 1, 1, 1. This is a very simple gradient field for every point on your three-dimensional space. You would have a vector pointing in the 1, 1, 1 direction. Yeah, that's right. So the computer program will generate it, and it will look a lot cooler than I could draw, because it just puts a lot of detail into it, and it draws everything to scale. Okay. So let's do a non-trivial example of a gradient vector field for the last 5 minutes of class. That way, we can actually get a concrete example in here too. This section was just kind of like, hey, this is the concept, and here's a bunch of applications for it. Not much concrete examples, but here's a concrete one. Let's say we want to find the gradient field for some function. Okay. Well, the gradient of this ends up equaling vector. So we got to take the partial derivative with respect to x, so this becomes 2y over here. And the partial derivative with respect to y makes this x squared minus 3y squared. There it is. That's our vector field. It is a gradient vector field. Now, what does this look like when you plot it? Doing this by hand would be very difficult. That's why it's very helpful to have those computer programs. And your vector field would look something like this. I mean, it could be done. You'd have to spend quite some time plotting the arrows and doing that, but it would actually be kind of cool if you didn't have anything else to do, you know? It'd be like a really cool, fun way to use your time if you had nothing else to do. But today, modern day human beings have developed technology to do this real quickly, so we can analyze it and move on and do other stuff. One last thing that is talked about in physics is the concept of a conservative vector field. I'll just tell you what that is defined, and then a conservative vector field is some f such that it's equal to the gradient of some potential function, where this f is the potential. It can be electric potential, it can be gravitational potential. And it's a conservative vector field if your potential function is scalar. So for example, the gravitational potential. It was, the gravitational potential was this. Why? Well, because when you take the gradient of this function, you should get the gravitational vector field. When you take the partial derivatives here, notice that this is the same thing as right? So then when you take its derivatives, what you end up getting is you get the negatives here. And you get this over there. And yes, you'd get that 1/2 to come down. The 2 would be here, but you can absorb it into one of the constants. But it allows you, let's say it's absorbed into the gravitational constant, you'd get what we had originally. So it's a conservative vector field because its potential function, when we take the gradient, we get the force field. That's that. Have fun in lab because you get to actually input stuff and have cool pictures come out of your making.
What day is this final?
Good.